Hello and welcome back. In this video, we will continue our work with static equilibrium, considering a more complex problem. Remember that the conditions for static equilibrium are listed here. The object that is in static equilibrium must have a sum of all forces acting on it add to zero. In addition, it must have a sum of all torques that are being exerted by those forces also adding to zero. Both of these conditions must be satisfied for static equilibrium. So the problem that we're going to look at is from our OpenStax text number 5 from chapter 9, and it reads as, repeat the seesaw problem for example 9.1. So please refer to 9.1. I've summarized the information here. With the center of mass of the seesaw 0.160 meters to the left of the pivot point, parentheses, on the side of the lighter child, end parentheses, and assuming the mass of 12 kilograms for the seesaw board. The other data given in the example remain unchanged. Explicitly show how you follow the steps in the problem-solving strategy for static equilibrium problems. So what I've done here is draw the picture that you will see in example 9.1. So you have a seesaw with a pivot point. Mass 1 is the mass of the lighter child, and mass 2 is the mass of the heavier child. The masses are given as 26.0 kilograms for the lighter child and 32.0 kilograms for the heavier child. In addition, we're told that the mass of the board for this problem, 9.5, has to be considered, and that's 12.0 kilograms. When you look back at example 9.1, you'll see that we assume the mass of the board to be 0 in that example. This adds a layer of complexity in including the mass of the board as part of the information, because notice if the pivot point is not located right underneath the center of the board, then the center, the Earth's pull on the board will be exerting a torque about that pivot point. So this adds a layer of complexity. We know this distance from the pivot point to the center of the board, and so let's just write that as RB. RB is given in our problem statement as 0.160 meters. And so that distance is RB, and I'm going to define that when we redraw this board. So what we're going to do is redraw this board as a line, and now we're going to place all forces on that line that are acting on the board. So there is a force downward on the board that is M2G on the right end of the board, and on the left end of the board we have a force M1G down. So those are the two forces, and if I wanted to be technically correct, I should actually be drawing M2G as a little bit larger force because child 2's mass is a little bit larger. So that's a little bit better. We have a force being exerted by the pivot on the board upward. You'll see that in problem, or sorry, in the example 9.1, that force is being given a symbol FP. FP is just the normal force being supplied by the pivot on the board, and of course that is upward. And then the other force I need to include is the force of gravity on the board itself, and that's right in the center of the board, and so that's the mass of the board times gravity. Anytime you have an object that is symmetric, the center of mass of that object will be in its geometric center as long as it's symmetric about its center. So we can apply the force of gravity acting on that object at one point, and that's going to be at its center of mass. So the center of mass of the board is directly in the center. I can apply the force of gravity on the board directly in the center. All right, so these are the forces acting. When I apply the first condition for equilibrium, when I add up all of the forces and set them equal to 0, I can just use positives and negatives to keep track of the direction part of these forces because they all lie along one line. So I'm going to call up positive and down negative as we traditionally do. And so this is going to be FP minus MBG minus M1G minus M2G. And that sum of all forces must add to 0. So that's our first equation that we get from applying the static equilibrium conditions. The second one is going to be summing all the torques and setting them equal to 0. And again, we can use positives and negatives because all of the torques being exerted by forces that lie in the plane with vectors r that also lie within the plane of the board are going to result in torques that are either directly out or directly in. So those lie along one line. So we're going to say out of the board is positive z, into the board is negative z. So let's look at these torques. So let's sum our forces. We can pick any point we want to, or sorry, sum the torques. We can pick any point we want to sum the torques about. And the place I'm going to pick to sum the torques is going to be this point right here. When you pick a point where a force is located to sum your torques about, then you get rid of the force that is located at that particular point from your sum. So in other words, there is no torque being exerted by this force Fp about this point because that force has an r value of 0 with respect to this point. So this is going to be our summing point for torque. You can pick any point you would like to sum your torques about because the sum of the torques about every single point on this board must be 0 or else this board will not be in static equilibrium. So we could pick this point, this point, this point, this point, this point. We can pick any point we want, but it's wise to pick a point where a force lies to eliminate that force from your equation, making it a little bit more straightforward to solve. Okay, so we're going to have 3 forces that are exerting torques about this point. One is going to have an R value, RB, that looks like this. The other one is going to have an R1 that looks like this. And then the last one's going to have an R2 that looks like this. So there are the 3 lever arms that are from the axis of rotation to the points of application of the force. So now we're ready to go ahead and sum up our torques. And so let's start with this, with the mass of the board as the first one. So the magnitude, or first of all, the direction part, R cross F, it's going to be out of the board. Out of the board is a positive Z. So this is going to be R, B, M, B, G. And this is going to be out of the board, so it's going to get a positive sign. This is all going to lie along the z-hat directions, and the z-hats will all cancel. So let's just use positives and negatives just like we did along the y-axis in writing the sum of the forces equation. Notice we didn't write y-hats here. They would all cancel. Anyway, we just use the positives and negatives. We're going to do the same thing for the z-axis. So this is a positive torque. In other words, it's out of the board, so I'm giving it a positive sign. Times the sine of the angle between R and F, and of course that's 90 degrees. Okay? The next torque is going to be due to M1G, so R cross F. That again is another torque out of the board, so it's going to be positive. So this is going to be plus R1 M1G sine 90 degrees. The angle between R1 and the force is 90 degrees. And now we need to take care of this last torque. And so R2 crossed into the force, that is going to be into the board. So it's going to get a negative sign minus in the magnitude R2 M2G times the sine of the angle between R2 and the force, and that also is 90 degrees. And that sum has to be equal to 0. So there is the second equation that must be satisfied for static equilibrium. So in this problem, we want to solve for R2 and we want to solve for FP. We're not explicitly asked to solve for FP in the problem statement, but in the example, you are asked to solve for FP, so it's worth going ahead and solving for it as well. We'll just come back up to this equation. And actually notice that we know all three of these masses, so we could immediately solve for FP from that equation. But first of all, let's solve for R2. R2 is going to come from this equation right here. Notice that all these sine 90s are 1. So I know RB, I know MB, I know G, I know R1, M1, and G. I don't know R2. I do know M2 and G. So there's just one unknown here, and I'm just going to isolate it right away. That unknown is the R2 that I want to solve for. So R2 is going to be equal to, when I move this to the other side, it's going to get a positive sign. I'm going to have these two left on one side of the equation. So this is going to be RB, MB. Now notice that these G's will all cancel. And of course, the sine 90s all go to 1. And so we're going to have RB, MB plus R1, M1. And then we're going to need to divide by the M2 to isolate the R2. I skipped some steps here. If you feel like you didn't understand how to isolate R2, please make sure you go through the steps that I skipped and make sure you have a good solid understanding of them. All right, so now going ahead and plugging in values. RB is 0.160 meters times MB, which is 12 kilograms. And then we're going to subtract, or sorry, add R1. R1 is 1.60 meters times M1, which is 26.0 kilograms. And now we're going to divide by M2, which is 32.0 kilograms. So R2 then is going to be equal to, pull out our calculator, 0.16 times 12 plus 1.6 times 26 and divided by 32. We're going to have 1.36 as the distance M2 must be from the pivot point, which is where we chose our summing point. This distance right here must be 1.36 for this board to be in static equilibrium, for there not to be a rotation about this point. So 1.36, 3 figs is what we were looking for, so this is exactly what we would express. So there is the answer to part A. Part B, again, it's not explicitly stated in 9.5, but it is in the example 9.1, so we're going to go ahead and calculate it. It's very simple. What is the force having to be supplied by the pivot point to ensure static equilibrium's first condition? So FP then must be equal to, notice that when I move these three terms to the other side, they'll all get positive signs and G will be in common. So I'm going to factor out the G and then I'll just have the M1 plus M2 plus MB. So this is going to be 9.80 meters per second squared. And now when I add these masses up, I'm going to have 26 plus 32. That's going to give me 58. And when I add 58 to 12, I'm going to get 70. So this is going to be 70 kilograms. So what is the magnitude of the force FP being exerted upward on the board by the pivot point? So 9.8 times 70 is going to give us a value of 686. And the units, meters per second squared times kilograms, are going to give us units of newtons. So this gives us an idea of how to solve a more complex problem applying the conditions for static equilibrium. Static equilibrium is incredibly important for engineers, architects, ensuring that things aren't going to be in states of rotation or changing their state of motion. Inherently important in making sure that buildings are sound and secure structures for us. So gives us a great idea of how to layer on one piece of complexity, and we will continue from here in the next video.